Now I want to take a look at a useful theorem called the nth term test. And if you look there, it says that if you take the limit of the terms, not the partial sums, but just the limit of the terms, if you're looking at the terms that you're adding up, if those aren't headed to 0, then the series diverges. And I think if we look at an example, it's kind of intuitive what it's saying there. Here's an example. N from 0 to infinity of n over n plus 1. Let's just write out a few terms first of all, just to kind of think about this. When n is 0, well, it's 0. And then when n is 1, you're at a half, then 2/3, then 3/4. Now, we know from limits, separately, let's maybe look at what is the limit as n goes to infinity of n over n plus 1. Now we know from algebra that, again, you can just look at the ratio of those lead coefficients because they're first degree. But I want us, it really is indeterminate form, right? Infinity over infinity. So I want to see you simplify algebraically. Don't just say that that limit is 1. I want us to show why it's 1. And once now you can see that that's going to 0. That limit is 1, right? So what does that mean over here? It means that we have this infinitely long sum, but eventually you are adding something that's basically 1, right? Very close to 1. Then you're adding something very close to 1. Then you're adding something very close to 1. So really, for large n, your sum is just 1 plus 1 plus 1 plus 1 plus 1 plus 1, something very, very close to that, right? So your running total is going to be increasing by 1 basically each time. So it's just running off to infinity. The only hope of a series converging is if eventually you're adding next to nothing, next to nothing, next to nothing. So if you're not eventually adding things very, very close to 0, you have no hope of converging. So when we take this limit, what I'd want you to argue then is that the key is that this limit is not 0, right? That's what the theorem says. If that limit is not 0, so we know then that our series, n from 0 to infinity, n over n plus 1, diverges by nth term test. One thing to keep in mind is the reverse is not true. If these are getting closer and closer to 0, so if you take that limit and it is 0, it doesn't mean that the series converges. Just think about the improper integrals we did. 1 over x headed down to 0, 1 over x squared headed down to 0, but one of those improper integrals diverged, one converged. And so it's not enough to just head down to 0. You have to head down to 0 fast enough. So just checking this limit and seeing that it's 0 tells you nothing. Could converge, could diverge. But taking this limit and seeing that it's not 0 definitely tell you that the series diverges. So what I'd like to do is take a look in Desmos at our partial sums. I just want to kind of see that happening here graphically. And so if you look on the left there, I've got the series that we were looking at, and I've just stopped it at b. And then the slider's letting b get larger and larger. So what we're seeing there, a is really my running total. It's a partial sum. There we are starting over again. And if you want to play around with this in Desmos as well, all you do is type in the word sum, and that sum symbol will come up, and you just plug in all the little pieces that you need. And for reference, I also plotted the line y equal x. Now, why did I do that? Well, remember, I just got done saying that eventually you're adding something close to 1, something close to 1, something close to 1. Well, what is that? That means eventually those partial sums have a slope of 1. Every time you bring in one more term, your running total goes up by basically 1. And that's what the line y equal x does, right? That's a line with slope 1. And so you can see that happening. The little partial sums are building up, and they're running pretty much parallel to the line y equal x. You know, it's not quite, right, because we're not adding quite 1, but, you know, we're adding 66 67ths, 67 68ths, numbers that are very, very close to 1, and getting closer and closer to 1 as we go. So we can kind of see that happening, and that's showing us that visually that series is diverging, right? It's not going to, that little green dot is not going to all of a sudden flatten out and have an asymptote, because all it's doing is marching along, going up basically by 1 each time. And we can see that by comparing it with the line y equal x. So I encourage you to play around with these in Desmos. Remember, a picture is not a proof, but it can help build up your intuition when you're first starting thinking about these things as to what's happening. So we got our partial sums running along there. We can even see what it is. Desmos is showing us what A is. That's my partial sum, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, basically going up by 1 each time. So there you have it. And unlike geometrics, there's really nothing as far as the form of a series that's going to make you think nth term test. Actually, I usually just check that first thing. I look at my a sub n's and I ask myself, is there any chance those are going to 0? If I can quickly convince myself that they're not, then I'll take the limit and run the nth term test. So when I look at that expression, I can quickly convince myself that that is not heading to 0, because n over n plus 1 we know goes to 1. So always be thinking of nth term test. It's one of the easiest things for us to do, and it can be applied in lots of different series. So always be checking for that.